Okay, so I am going to jump to the last problem now, which I haven't actually worked it out yet, but I know what I'm doing, so it'll work. I say that confidently. All right, so verify the formula for the resonant frequency for a parallel RLC circuit and for a series RLC circuit, and find the current for the following circuit as its resonance frequency. So this will pretty much review everything, so even if we don't get to the other stuff, we'll get to that. So once again, it's not pasted. All right, so first of all, we need to know what we mean by resonant frequency. So you've probably heard of resonance. You maybe have done it in a physics class. And a resonant frequency is the frequency at which you get maximum oscillation. So weird. Why would it not paste? Do y'all ever have problems like this with just like stuff that normally works all the time? All of a sudden I can't paste. Here, it's copied it, then always copies it. And now I go to paste it. And nothing. You know, it's because I'm sitting in front of a bunch of people and recording all at the same time. Okay, so resonant frequency means you have the maximum oscillatory response. So you have the maximum oscillatory response, and also not letting me type. Now, do you remember what I said resisted a change in current? Reactance. And what was reactance? Exactly, the imaginary component. If you want maximum oscillatory response, do you want to resist a change in current, or do you want to let current change a lot? Oscillatory, by the way, means going back and forth and back and forth and back and forth. You want it to change a lot, so you don't want to have reactance. You want to have, you want reactance to be zero, or in other words, the imaginary part of the impedance would equal zero. That is when you get resonance. When you have the imaginary part of the impedance equaling zero. And also at the resonant frequency, that's going to be where you also have maximum power, and you're going to talk about that later. So when the imaginary part of the impedance is zero. Now, does that mean, could you have just a capacitor and be at the resonant frequency? Because that has positive imaginary, and if I had just capacitor has negative J, and an inductor has positive J. So if I want to get zero, I can either have all real, just only resistors, or I could have my inductors and my capacitors cancel each other out. So let's say I have a series circuit and I want to figure out what my resonant frequency is. So I want the resonant frequency will be when the imaginary part of my reactance is 0. Well, the real, so this is in series, and I make this, so this becomes j omega L, and this becomes minus j over omega C. R remains R, and V is whatever phasor it is. The real part of the impedance is not going to affect what my resonant frequency is going to be, because the real part is not the part that's at issue. The part that's at issue is this imaginary part. I want the imaginary part to equal 0. So I have j omega L minus j omega C equals 0, or j omega L equals j over omega C. By the way, this right here, that's the Greek letter lowercase omega. It looks like a W, a lowercase w, but when we're talking about frequency, it's an omega. And if you're confused, that's the uppercase Greek omega, and this is the lowercase omega. And usually when we write omega naught, that's what we mean by resonant frequency. You might see other symbols for that. So j omega L equals j over omega C. I'm solving for omega, so I'll multiply both sides by omega C. And I get j omega squared L C equals j. I can divide both sides by JLC. And I get omega squared equals 1 over LC, or omega equals the square root of 1 over LC. So for a series RLC circuit, the resonant frequency is the square root of 1 over LC. Let's look at a parallel. Okay, so we want the imaginary part of our impedance to be 0. So would it make sense to you that this part of the circuit is the only part that can make the imaginary part equal to 0? Because that's got the imaginary, the components with the imaginary in it. So whatever these two are combined, so whatever these two are in parallel, if I get something imaginary here and I put that in parallel with something real, I'll still have something that's got an imaginary component. So I want to make this part equal to 0. So I want to make j omega L in parallel with minus j over omega C equal to 0. Well, how do I do things in parallel? Product over sum. So j omega L times minus j over omega C over j omega L plus minus j over omega C. Okay, now I don't like this complex fraction, so I'll multiply the top and the bottom by omega C, and I get j omega L times minus j over j omega squared LC minus j like I'm missing a J somewhere. Oh, no, no, I'm not. Okay, so then this was multiplied. J times J is -1 because it is the square root of -1. So J times J is -1. So negative J times J is +1. So this is omega L over J omega squared LC minus J. I'm not going to be able to make this work this way. Give me a second. Let me see what I get. Okay, so I want to get the J out of the denominator, so I'll multiply by J over J. And I get omega LJ over omega squared negative omega squared LC plus 1. I have to think about this and get back to you, but I know that what happens is I get 1 equals omega squared LC, and 1 over LC equals omega squared, and omega equals the square root of 1 over LC. I thought it would just fall out naturally. I knew I would get exactly the same thing I got the other time, and somehow or another it didn't happen. So it's the proof that didn't quite work, but it came real close to working. But the result is very useful. So if you have whether a series or a parallel RLC,
the one over that one over that one.
And it did work out?
Yes.
Yeah, okay, all right. Yeah, that makes sense. Yeah, okay, I'll use that and I'll put a video about it later. Yeah, okay. So just rather than doing, well, I will explain it. I'll get it all there. Usually what I do, but I didn't do it this time because I thought I'd be clever. Usually what I do is I take all 3 of them, and then I set the imaginary part equal to 0, and then it works. But this time I thought I'd be clever and just do the imaginary part. But if I just set this imaginary part equal to 0, right now I'm not quite getting it, but I will get there. But the key point is that the resonant frequency is the square root of 1 over LC. So once you have that, it gets pretty easy to answer the question, which was, we said verify the formula for resonant frequency. We did. Find the current for the following circuit at its resonant frequency. So we know the resonant frequency is going to be, let me try one more time. Can someone just tell me what my values are?
Voltage is 20, resistance is 18, capacitance is 14, and then inductance is 2.2.
0.2. So capacitance is 14, farads, inductance is 0.2 henries, resistance is 18 ohms, and voltage is 20 angle 0?
Yes, ma'am.
Okay. All right. So we know that the resonant frequency is 1 over the square root of LC. So it's 1 over the square root of 0.2 times 14 which is 0.597, 0.598. Now, we know that if I redraw this in the phasor domain, that the resistance remains 18, the capacitance will be minus J over omega times 14, and the inductance will be J times omega times 0.2. So if I take minus J over 0.5976 times, what was the capacitance? 14. I get, I apparently am in the mode, polar mode. I'm going to change this to rectangular mode. And I get minus 0.12 J, or minus J 0.12. And if I take J times omega times the inductance, I get 0.12 J, at which point you say, oh, of course I do. Why do I say, of course I do? Because it's supposed to be in resonance, right? And so my positive imaginary part and my negative imaginary part are supposed to cancel out. Okay, so now if I do product over sum, that would give me an error if I did product over sum with all of these. But if I did 1 over 18 plus 1 over minus J 0.12 plus 1 over J 0.12. You remember that formula for doing things in parallel? 1 over, 1 over. So if we do that, 1 over 1 over 18 plus 1 over, or is J over, no, it wasn't, it was 1 over. 1 over J.12 plus 1 over minus J.12, and you'll see those last two will cancel out, and not surprisingly we get 18. And so we get 18, and so to find the current, I think that was what the instruction said, find the current through here. Now I just have V equals IR. I just have 20 volts and a resistance of 18. So V equals IZ, 20 equals I times 18 ohms. I equals 20 over 18, just 10 over 9, which is something. .111. And that is all I have time for, but that should really help you figure out what you need for your quiz. I mean, so now it should become easy. Yeah.
I just have one quick question. When
Sure.
you mentioned there's a oscillatory response, what exactly is that response? Is that a voltage?
It could be voltage or current, but they're related to each other. So oscillatory response, so the response that is going to be, we're going to be talking about either voltage or current, one of those two, and just they're both going to be oscillating. And when I say the most oscillatory response, it means oscillating the most. So yeah. Other questions?